A single chunk of this natural element contains a terrifying duality. It can generate enough electricity to keep a metropolis lit for years, or wipe a city off the map in a fraction of a second. Yet, for over a century, the source of this immense power hid in plain sight as an unremarkable, heavy black rock known as pitchblende. In 1789, the German chemist Martin Heinrich Klaproth decided to analyze this rock. He dissolved it in acid, heated the residue, and extracted a strange black powder. He had identified a completely new element, which he named uranium, in honor of the recently discovered planet Uranus. It took another 52 years for Eugène Melchior Péligot to isolate pure uranium metal, but no one had any clue what to do with it. Its only real commercial use was as a decorative additive, creating glassware that gave off an eerie bright green glow under ultraviolet light. People were casually drinking out of radioactive goblets. Early chemistry could only examine the physical exterior of the element, completely missing the massive well of energy locked just beneath the surface. In the winter of 1896, French physicist Henri Becquerel planned to expose uranium salts to sunlight, hoping to see if they would emit X-rays. But the Paris sky was cloudy. Frustrated, he wrapped his photographic plates in thick black paper, placed the uranium salts on top of them, and shut them in a dark desk drawer. A few days later, he developed the plates on a whim. Instead of a blank sheet, he found dark, heavy imprints of the uranium crystals burned right into the film. The salts were emitting their own powerful energy, completely independent of the sun. Through a purely accidental change in the weather, Becquerel became the pioneer of a strange, invisible subatomic force. Marie and Pierre Curie soon picked up the investigation. They noticed that raw pitchblende emitted far more of these rays than pure uranium. By meticulously siltering tons of the rock, they discovered two entirely new, highly active elements, polonium and radium, and they gave this strange radiating phenomenon a name: radioactivity. Radioactivity proved that atoms were not solid, inert little bricks. They were active machines, forcing physicists to look deeper into the center of the atom to see what was generating these invisible rays. By the 1930s, scientists had discovered a new tool, the neutron. They realized that by firing these newly discovered subatomic particles like tiny projectiles, they could strike the nucleus of an atom and alter its structure. In 1938, Otto Hahn and his assistant Fritz Strassmann set up an experiment to bombard uranium with neutrons. Their operating assumption was straightforward. The massive uranium atom would absorb the incoming neutron and become a slightly heavier element. Instead, the chemical results of the test made no sense. They didn't find a heavier element in the debris. They found barium, an element that possesses roughly half the atomic weight of uranium. Hahn sent his bizarre findings to physicist Lise Meitner. Running the numbers, Meitner deduced exactly what had happened. The neutron hadn't stuck to the uranium. It had struck the nucleus with such force that it cleaved the atom perfectly in two. Science had finally broken the atom open. They called the process nuclear fission. But splitting the atom immediately presented a glaring mathematical paradox that seemed to violate the basic laws of physics. When you measure the resulting fragments of a split uranium atom, the math doesn't add up. The total mass of the leftover pieces is slightly less than the mass of the original unbroken atom. Some of the physical matter simply disappears. But as Albert Einstein had already established with E equals mc squared, mass and energy are interchangeable. The missing mass hadn't vanished. In the exact moment the nucleus fractured, that tiny amount of physical matter instantly converted into an intense burst of pure thermal energy. Alongside this heat, the fractured nucleus ejects 3 free high-speed neutrons. If these hit neighboring uranium atoms, they also split, releasing energy and firing off 9 more neutrons, then 27, then 81, all in a nanosecond. This specific subatomic architecture turns a single fracture into a self-sustaining chain reaction, scaling a microscopic event into a massive release of power. Natural uranium contains different isotopes. Over 99% is uranium-238, 0.72% is uranium-235, and uranium-234 barely registers. You can't trigger a chain reaction with any isotope. Abundant uranium-238 simply swallows stray neutrons. Only the extremely rare uranium-235 fractures on impact to sustain a fission chain. In just over a century, humanity progressed from marveling at a dense rock that could make glass glow to isolating the precise isotopes required to trigger and control a nuclear chain reaction.